Hello everyone, this is Riley, and today I want to show you an overview of the Multivariable Calculus course. And as a disclaimer, I will not be going through any specific examples or formulas. I will mostly just cover the main ideas. Before or during you taking this course, it's important to understand the meanings of these concepts instead of just knowing how to calculate them, which you'll get plenty of that practice during the course, I assume. And I divide this course in 3 sections. First is the 3D vector space, since you're going to be working in 3D, and you're going to have an introduction in that. And then you're going to move on using all these concepts, using do partial derivatives and integrations, specifically double and triple integrations. So first you're going to be introduced to 3D vector space. Usually when you see, there's a right-hand rule here. So usually when you read a graph in 2D, it's like this. So x and y, right? X and y is x-axis, y-axis. But in 3D, it's like this, which you usually see. You see the z-axis, x-axis, and y-axis, and that's how usually the graph is given. It's never given this or this or this. It's in this orientation that it's usually given. So that's important to keep in mind. And first, you're going to go into the dot product, which is it's when you input 2 vectors, it's going to output a scalar. Which that scalar is a measurement of alignment of these 2 vectors. So for example, if 2 vectors are parallel, the dot product would be 0. And through dot product, you'll be able to measure the length of, for example, a vector, and even the angle between the vectors. And after that, you're going to go into cross product, which is A cross B. It looks really like a multiplication sign, but it's not, because it's between 2 vectors. And when you cross product A and B, you find the vector that is perpendicular to both of them. So orthogonality is basically another word for a fancy word for perpendicular. So for example, if this is A and this is B, so A and B are, for example, like this. They're not parallel to each other. If they're parallel to each other, it's 0. Their cross product would be 0. So they will be at a certain angle intersection. And then what you'll find that is A cross B, it will be the vector. This would be A cross B, the vector that is perpendicular to both of these vectors. So this would be A, B, and then this would be A cross B. So that's the main concept of it, and you'll be able to use this to find volume of trapezoid, and you'll be again find the angle between the 2 vectors. So these 2 are the fundamental operations in 3D vector space. And going on, you're gonna learn how to find the plane, the function of a plane, and the lines in 3D. Planes, you're going to use normal line and find the plane, the function of the plane, and so is lines. So you're going to do some problems on the intersection between them, and where does it intersect, how do you find a plane using just 3 points, given 3 points, etc. And moving on, we're going to learn about a lot of shapes. So you're transforming a shape from 2D to 3D. For example, if like a circle in 2D, if the same exact equation in 3D, it will be a cylinder, because then there's an extra axis where it just infinitely multiplies. It doesn't. And similarly, if you want to find a sphere, it would just be x squared plus y squared plus z squared equals r squared. That's quite simple. But you're gonna go into a lot of funky shapes. Some like ellipsoid, cone, elliptic, parabola. So parabola, but that's like this. Elliptic parabola, hyperbolic parabola, paraboloid of 1 sheet, and paraboloid of 2 sheet. You're gonna learn that like shapes that's like Pringles, the shape of Pringles, the shapes of an egg, just a lot of funky shapes in 3D. And it's very important in this section to visualize. I mean, your professor will probably have a very hard time drawing all these shapes, because how can you draw a 3D shape on a 2D board? But I highly encourage you, when you study this, to search up images online of these different shapes and use traces. Traces is basically compared to 2D. So basically, when you 2D, where you're trying to graph, for example, a parabola, you're trying to have a rough graph of parabola. You're gonna enter x and y and find if, for example, x is 1, y is what, x is 2, y is what. So in similar fashion, traces is that method in 3D. And you'll be using traces to create a visualization for each of these shapes. And then next going on, you're going to learn about curves. So just lines in the in 3D. So I should go over this first. You're gonna learn about unit tangent vector and unit normal vector and binomial vector. What it means is that, for example, if you have a curve here, my pens here have a curve. This is a curve. Just imagine it's continuous. It's continuous in some directions, and the tangent vector is very simply just the vector that's tangent to it, and the unit tangent vector, meaning that the length of this vector is 1. And so you're gonna have a unit tangent vector, and imagine if this curve is curving this way. You're also gonna find the unit normal vector, which is like this. And unit normal vector is the normal line in the direction that it's bending. And lastly, my hands are getting stuffed. Lastly, you're gonna find the binomial vector, which is a cross product between the unit tangent vector and the normal vector, and that's called the binomial vector, and it'll be like this. So whenever you'll have a curve, you have these 3 lines in mind, and these are kind of tedious calculations, especially finding the normal vector and binomial vector. Oh god. You're gonna have a very fun time with them if your professor gives you some funky numbers. Anyways, using these, you can find the arc length. Arc length is very self-explanatory. So a length of a curve, the length of a certain curve in a certain interval, and the curvature, how much it curves. For example, a helix has a constant curvature because it's always have the same curvature. Like the helix. The torsion is basically when the curvature is not constant. And when the curve is moving in different directions, its unit tangent vector, normal vector, and binomial vector will also be like twisting, and then torsion will be the measurement of that. And this wraps up the first part of the introduction for the 3D vector space. Now we're going to go to the partial derivatives. Partial derivative is definitely a more interesting part of the course. Look at all these symbols. It's like interesting. It's like the gateway to mathematics, higher mathematics. At least it was to me looking at these symbols. But after I learned it, it's just pretty normal. It's just derivatives. Anyway, so let's start with level curves and countermap. So when you use countermap is basically when you see a topological map of the world, which I think I will show one here, and you'll be able to see from this 2D map where the mountains are tall or it's low sea level. So that's just, it's the same thing for a function when it's given to you. It can also have a countermap. You can draw out the countermap and see where it has the maximum or minimum, or where it's tall, low, and everything like that in the 2D. And level curves are just specific curves within that countermap. So a countermap will have a lot of curves. It will have, so this is a level, this is a level, this is a level. So each of these level are level curves. And countermap is a collection of all those level curves. And then we're going to go into limits and continuity. Limits and continuity here is different than Calc 1, is where in Calc 1 you're just a line. It's a line, and you're just asking if limit or continuity, does the limit exist at a point on a line. So you just test the right hand side limit and the left hand side limit, and you'll be able to know if the limit exists or does not exist. But when we're talking about 3D surfaces, if a limit exists at a point on the 3D surface, we need to test through multiple lines, not just one line, because that would not be sufficient enough to prove that limits exist or not exist. So in order to prove a limit does not exist, you have to use a multiple lines that is on that surface that pass through that point to test if they all equals to each other. If they do, the limit exists. If it doesn't, the limit does not exist. And same as continuity. And then this is the star of our show, partial derivatives. This is a funky looking D. It's not a Greek letter. It's called del f over del x, and it's the same meaning as f partial x. So it's like dy dx equals to y prime. It's the same idea. How do you find partial derivatives? Basically assuming that a multivariable function, if your f has x and y, and so if you're trying to find the derivative respect to x, you just assume y is constant, and vice versa. If you're trying to find the f partial y, you just take the derivative of y and then assume x to be constant. Treat x as a constant number. So an important theorem in this unit is I think it's called Clairaut's theorem. So it's when a multivariable function f first takes partials respect to x and then respect to y. So you take partial of x, assuming y is constant, and then use the result, take the partial of y, and assuming x is constant, is equal to the vice versa, where you take the partial of y and then x. So this is important, and you're probably gonna use this in the max and mins test later. And then you're also gonna learn about chain rule for multivariable and implicit differentiation. So you remember when in Calc 1 you have this function that given to you with x and y in it, and you're supposed to differentiate all with respect to x or y, and then you find dy dx and using a bunch of algebraic operations. But then after you understand partial derivatives, there will be given to you a formula that can just do that for you. You don't have to go through all the algebraic operations. And then we're going to go into tangent planes and total differential. So when we're in Calc 1, we find the derivative at a point. That derivative is just the slope at that point, and then we still need to find the tangent line. Same as here, we're going to find the tangent plane of that point, and we're going to use, as we previously learned, cross product, I think, and to find a normal vector to find tangent plane. Total differential is very similar to linearization in this case. How much does z change when you alternate x and y? So, for example, you have a surface, and then when you move left and when you move around a point, the total differential of it is like basically how much does z change when you alternate x and y, when you change the values of x and y. And that's the main gist of it. And you need total differential in the future. For example, in differential equations, you need it for solving exact equations, first order linear equations. And then we're going to go into gradient vectors. Gradient vectors of a surface is basically you take the partial of x, z, and y of this surface and put it into a vector, and then plug it into a point. So it becomes a vector. And what does that vector mean is that it's, for example, this is a surface, and the gradient vector of this point is just the normal vector at this point. So gradient vector is known as a upside down triangle, and then f is orthogonal to the level surface. So this is important in later using to calculate Lagrange multiplier. And also gradient vector helps you find the direction of fastest increase. So if you have a surface and you're at a point, and then you're trying to find which direction has the fastest increase in the slope, and you're going to use gradient vector for that. And now you're going to try to learn how to find the maximum and minimum of a function, just like you try to do it in Calc 1, except when you're trying to find the local maximum and minimum, you're going to have a test. Basically, you're going to compute a bunch of partial derivatives, and you're going to run it through a test, and you'll be able to know which critical points are local maximum or minimums. And when you're trying to find the absolute maximum and minimum, you're just going to compute all the critical points, including on the boundaries, and try to find which one's the biggest. You just compare all of them. It's really boring and tedious calculations and stuff. And so and then we're gonna try to find the Lagrange multiplier, which is an important concept in optimization, which you're trying to find the maximum and minimum with constraints. So within this bounded area, with this constraints or two constraints, you can have many constraints. Within the constraints, where is the maximum and minimum? And you're gonna use level curves for that, and also gradient vector. And this wraps up for the partial derivatives. Now we're gonna go to integration. I find it quite challenging to explain double and triple integrations without you knowing how to operate this, or without you knowing like the order of integrations, or some basic knowledge of it, but I'll try my best. So for double integrations, you're integrating a function with two variables, x and y, and you're going to be given a bound, which is a, b, c, d. So you're going to have a surface and a bound. And what you'll find after the double integration is a volume below the surface within the bound. So when it's over a double integration over rectangles is when a, b, c, d, the bounds, are numbers instead of a function. When they're numbers, they form a rectangle, and then you find the surface in that rectangle, the volume of the surface below the surface. You'll find the volume below the surface within that rectangle. But you don't always want to find just within that rectangle. You want to find what about in a general space. So over general region is when you use, instead of c and d, you plug in functions. So I'll show some pictures here how what's the difference between type 1 and type 2, where you have two functions with respect to either x or y, and then you're gonna find the the region between them, and then that would be a general region, and you can use that to find the volume of the surface below that bounded region instead of a rectangle. But if your bound is a circle and it's not a rectangle, it's hard to be classified into type 1 or type 2, because if you classify into 1, the function will be something like root 49 plus x squared. That you really don't want to plug it in and try to integrate that again, and that's just too much of a hazard. So you will convert the whole function into polar coordinates. So instead of f of x and y, it will be f of theta and r, and then in polar coordinate, you'll be able to find the surface of the volume of a surface within the bound of a circle, or something a polar shapes, like any polar shapes that is hard to find using the previous methods. And now moving to triple integrals, where you're going to be given is a volume function of a surface with three variables, x, y, and z, and then you're going to do the integral 3 times. And the main point in this unit is to convert the given function into different coordinates to find them easier, basically. First, you're going to learn how to find it in cylindrical coordinate, which is basically polar coordinate but in 3D. So polar coordinate has theta, r, and in cylindrical coordinate you're going to have theta, r, and z. So instead of x and y, it's theta and r, and z, it stays the same, so it's a cylindrical coordinate. You also learn how to convert the function into a spherical coordinate, very self-explanatory, spherical coordinate, so it's using spheres. And instead of x, y, and z, you're gonna find rho, theta, and rho, theta, and phi. So these are the Greek letters that is a measurement of this coordinate. So rho is the distance from the origin to a point in spherical coordinate. So it's the distance. Theta is very similar in cylindrical and polar coordinate. It's the angle from x to the point, so x to the point. And phi is the angle from z, so remember z, from z to the point. So these 3 measurements is sufficient to find a point in spherical coordinate, and you'll convert this whole function into spherical coordinates for your convenience to solve it. And then lastly, we're gonna look at change of variables, basically changing into whatever coordinate that is convenient to you. So you can make for example, a trapezoid that's an x and y and z into a square in your new coordinate by change of variable. The most important thing to remember is that when you're given a function of x and y, it's a surface. It's a 2D surface. And what you'll find after integration is 3D. Okay, it's the volume under the surface. But when the function is, it's not a function. When it's a 1, you're going to find the area of the given boundary. So this is what is very interesting. And in triple integrals, you're going to be given the function of a surface, a 3D surface. And after integration, you're going to be finding a hypersurface, like a 4D, basically a 4D hyper object. So But when you equate the function is not a function, is instead of 1, then you find the volume of the boundary. Okay, so this is very important. So don't get confused with when it's a function and when it's 1. When it's a function and when it's 1. Okay, so just like when you have one integral, it's given a line, you find the volume, the area below the line. And when you integral of 1 is just simply x, it's just simply the line. Okay, I think that's a very important concept in integration. And this is an overview of the multivariable calculus class. Thank you for watching. If you have any questions, please leave a comment below. I will answer them. And if you have any suggestions for how to make a video better, also please comment below. And I hope you enjoy your Calc 3 class and pass them, hopefully. It was a fun class to learn all these new things, and see you next time. Bye bye.